Hi students, this video is on periodic trends. In this video you'll learn that there's a periodic trend for atomic size. You'll also learn that there's a periodic trend for something called electronegativity. We'll start with a video. In this video you've got three different metals that are being added to beakers of water. There's nothing special about the water, it's just regular water. And really what you're seeing is the reaction that happens when an element called lithium is added, there's its symbol, to water. They've also, I think, added an indicator which doesn't affect the chemical properties of the water or the reaction that the metal has with it, to show that there's a reaction taking place and it's changing the acidity of the water. But that's not the biggest part of the reaction. The big part to watch is that you're adding this metal to water and it's causing it to run around and create hydrogen gas. There's also a metal here called sodium, and then this one that's exploding over here is called potassium, and those are the chemical symbols. Now, why am I showing you a video of these three metals as they react in water? What's so special about these three metals? Well, long ago, Dmitry Mendeleev, who's pictured here, discovered that if you arrange elements in increasing atomic number, really he did it by atomic weight, but atomic number is ultimately what he was doing, and you use these series of rows and columns, you could develop a regular and repeating pattern of elemental properties, both in their chemistry and how they react chemically and what they did physically, how they behave physically. So when arranging them this way, you can show how the elements are kind of related to each other by families. So to show this a little clearer, what I'm saying is that numbers 1 and 2 are up at the top, and then we go 3, 4, 5, 6, 7, 8, 9, and 10, and then starting over again at 11, 12. This repeating pattern of reactivity occurs when you put these different elements on top of each other in what's called a column, or another word that we use in chemistry is, actually that's just one L, apologize, column, is a family. So families, columns, these are the groups, really is actually probably the most common name we use for it, of elements that all have similar properties to them chemically. Another thing that is a periodic trend is not just down groups, okay, but across periods. So the periods go in this direction. Period 1, 2, 3, 4, 5, 6, and 7. There's a repeating trend that we'll see that occurs across periods, and other repeating trends that occur down groups. So knowing those trends can be helpful for concepts later in chemistry. So that's what we're talking about when we say periodic trends. Just to give it in a little more concrete language that you could copy down, the idea of periodic law is that atoms with similar properties appear in these groups or families on the periodic table, though they also occur in the rows or the periods. But when we're talking about chemical properties, things that you could observe in like a reaction, everything that's in a group or a vertical column occurs down in a trend down this way. So that all these elements do the same thing. All these elements do relatively the same thing. And that's generally true as you go down the periodic table, down these families. Now, I'd like you to have these arrows drawn into your notes in one way, shape, or form if they're not there already. I'll give you about 10 seconds to pause the video and draw this. Take your time so that it's in your notes and it's clear. You'll need it. Now, the first one we're going to talk about is called atomic radius. And it's demonstrated here, but I'll show you using a gizmo as well. And the idea with this is that the larger elements occur as you go down a group. Okay, and this makes sense, right? As you go down groups, the elements get bigger. And that's not just, though, because that they're getting larger in their atomic number. Because if that were true, then they would also get bigger if you go from left to right. But they don't. They actually get smaller as you go from left to right. That's odd. But if you remember, the way that we drew these arrows were that we remember that the blue arrow is going right to left. So it's actually becoming larger as you go more towards the left side of the periodic table. You'll notice briefly, just I'll make a note here, that there's a break in the periodic table here. It doesn't look like a typical periodic table. What's happened is we've cut out the center of the periodic table right here. We've cut that whole section out and just kept the sides. This is called a simplified periodic table, and it just makes it easier to look at a particular subset of the elements. That middle set of the elements isn't quite so relevant to the periodic trends we're interested in right now. They kind of they're more of an exception to the rule. The idea of increasing atomic and decreasing atomic radius still generally holds for those as well. To show you why this makes sense, actually, I'll put it in words first, and then I'll show you the visual. We're giving you the idea that it increases, atomic radius increases as you go down a group, and that is indicated by this arrow, and it decreases as you go across a period from left to right. Or you could say it another way. Instead of decreasing, you could say increases as you go across a period from right to left. Just depends how you look at it. But we're showing it to you here. It's increasing from right to left. Or you could say it decreases as you go from left to right. Just depends on your perspective. I'm going to show it to you the way that it was originally written here, is decreasing across periods. But again, the perspective matters. So going down a group. If I start in group 1 and I go down, you'll notice as I went from hydrogen to lithium, just one cell below, one element square below, I got a larger atom. Lost my cursor here. As I go down from lithium, I get to sodium and I get a larger atom again. I get larger as I keep going down. So it's increasing in size down groups. Without going into too much detail, the reason for this is because we're adding on a extra energy level of electrons. And that's indicated by the growing rings that are added to the outside. Here we have 1 ring, and then here we have 2 rings, 3 rings, and so forth as we go down. As you add a ring, you add distance between the middle of the atom and the outside. That's what atomic radius represents, the distance between the center and the outside. As I go from left to right, I'll notice as I go across a period, let me grab one that has more elements, period 2. As I go across the period, there are no elements here, I find that the elements get smaller in size. Now I'm going to go down a group and show it again. As I go across period 3, from left to right, the elements again shrink in size. Okay, so the question is, why does this happen? The main reason that it increases in size going down a group is the concept of the increasing energy levels. Okay, so it's increasing in its energy level as it goes down, and when you add an energy level, these rings, effectively, you're getting you're getting more distance between the center and the furthest out electrons, what we might call valence electrons a little later in the course. So 1 energy level here, 2 energy levels here, and so forth. Why, though, does it get smaller when you go from left to right? What is the reason for that pattern? Well, the reason that it gets smaller when you go from left to right is because you're adding on protons. Okay? And when you add on protons, you're adding in more of the positive charges that draw in the negative charges. Think about this. Even though you're adding negative charges too, you're adding electrons every time you go up in atomic number. As you go from left to right, you add one more proton every single time. So if you add another proton, you're increasing the amount of the charges that are in the center of the atom, and that's pulling in on the electrons that are surrounding it. Also, because you haven't added any extra energy levels, you're still dealing with the same number of energy levels. You aren't making the distance jump out any further. You're basically pulling the electrons from that outer energy level and you're bringing them towards the center. So that's the main reason that the atomic radius shrinks as you go from left to right, and why it jumps up as you go from top to bottom is because of the energy levels either staying the same or increasing in number, and because of the number of protons in the center increasing as you go from left to right. The second property that we're going to go over is called electronegativity. And it's a kind of a fancy word, but you want to just think about the word electro in here. That means that we're talking about the electron. Okay, the word electron's even in there. Electron is in there. We're talking about electrons here. This is a measurement of how attracted the what we call valence electrons, or the outer electrons are towards the nucleus. So if I go back a slide here, the valence electron is going to be this one right here. The valence electron in the second example here, there's actually two, this green one and this green one. They've actually made all the valence electrons in this example green. This element called boron is surrounded by 3 valence electrons. So the valence electrons are the electrons in that outermost energy level, or we might call the outermost shell. A little later in the course, we'll start referring to them as shells. So what's the importance of this? Those valence electrons have a particular attraction, just like magnets, because they're opposite charges, to the protons in the nucleus. The further they are from the nucleus, you can imagine the weaker that attraction, that pull on the nucleus is. And the further out you go from the nucleus with increasing energy levels, the worse and the weaker the attraction is between those outer electrons and the inner are to the nucleus. And another thing to note is that those electrons could be attracted to its own nucleus, okay? The atom of it that it is surrounded, or those electrons could be attracted to the nucleus of another atom when we're talking about chemical bonds. Because in the end, if you're going to make molecules, which is what life is made out of, not typically out of just one atom at a time, but you're making molecules and things that have bonds to them, in that case, you're dealing with multiple atoms interacting with each other. And that's when the chemistry gets interesting and fun, when you have 2 atoms interacting. And when that happens, their electrons also interact with each other. So the electrons in that case are either attracted more so to the element that they started from, or they're attracted to the element they're bonded with, or maybe a little to both. We'll talk more about that when we get into bonding. So when 2 elements are interacting, they're going to fight over who gets the electrons, because the positive charges in each of the nuclei are going to kind of fight over the negative charges that they're surrounded by. And they'll pull with that force, the electrostatic force, on those electrons, and they'll pull on each of them. However, some elements pull harder than others. That's the big takeaway. Some elements pull harder than others on electrons. So which elements pull the hardest? Which ones want to hold on to their electrons the most? Well, the trend for electronegativity looks like this. And you have this drawn in your notes, hopefully. So the most strongly held electrons are with this element right here called fluorine. It's got an F. The least electronegative atoms are over here on the far left bottom. Here is a couple better ways of visualizing this. The most electronegative atom, as I said, is fluorine. So that's the most electronegative element, and its number is the number 4. Okay, you might remember this from doing a gizmo, and in that gizmo we had a property called electron affinity, and in this case I'll show that to you briefly. It's similar to that idea. Electron affinity, in this example, let's pull one that we said is the strongest element, fluorine. Its ability to desire more electrons is very, very strong. Its ability to pull an electron from another atom is very, very strong. Oxygen is also pretty good at it, okay? But some elements are not very good at it. They have to be really, really, really close in order to pull an electron onto them. Seen another way, it's the ability of the electron of the atom to hold on to its electrons and not get them pulled off. That's actually another concept called ionization energy, but it actually is pretty much the opposite of electronegativity. So we're not going to study that term, at least for our class in particular, right now, but ionization energy is very easy to think about. It's basically the opposite of electronegativity and how it works. So these would be the values that you use, and these values are actually very helpful because in the end, if you have elements that bond together, which happens all the time, H2O, right, is hydrogen and oxygen bound to one another. Hydrogen is a rather electronegative element. It's 2.1, kind of right in the middle. And oxygen is also a rather electronegative element. This means that they desire very greatly to hold onto their electrons and not give them up. So when they bond, they actually will share the electrons because they both want them kind of equally. However, if oxygen is bound to an element like lithium that has a very low electronegativity, rather than share electrons, oxygen will just grab them, and an element or a compound like lithium oxide will actually is L2O, but will exist as a compound like a crystal, and it will oxygen in this case will be stealing electrons from the element lithium. All this is explored a lot more when we study bonding, but you can see how important it is to study and to know how electronegativity works. Basically, the trend is it goes greater as you kind of go diagonal, or in other words, up and across the periodic table. Another way of visualizing it is by height, with the tallest being the most electronegative and the lowest being the least electronegative. So in this case, you can tell as you go up and over, generally the trend is electronegativity increases. And that's of course not completely consistent. As you can tell, copper and zinc are they have a slightly less electronegativity. Copper is 1.9, zinc is 1.6. So it's not like it's a perfect trend, but it generally increases as you go from left to right. And if I was to ask you which element is the most electronegative, potassium, K over here, or chlorine over here, you would know right off the bat which is going to be the most electronegative because you know which side of the periodic table tends to have the more electronegative elements. So that is electronegativity and atomic size and periodic trends. I hope that was helpful.